Welcome to Saxon Math, Lesson 114, Course 3. Now, we're going to be talking today about calculating area as a sweep. Now, I'm sure all of you have seen a broom before because we had one in the classroom back when we were in the classroom. Now, I want you to imagine a push broom. That's not the kind of broom that we had in the classroom, but it's the kind of broom where there's a stick coming out of a little flat piece with its bristles coming down. You may have seen these on those challenges on the internet where they balanced a broom. It's a push broom. Now, this pushes through a rectangular space and it leaves a clean area behind it when you push the push broom. If you push it across the dirty floor, then you will leave a clean spot behind it. Now, I've illustrated that in two different ways right here. Now, in this first way, we push the broom straight. We've just pushed it straight across. We've got the top of the broom, the bottom of the broom, and these are the same because we pushed it evenly across. We've got the width of the broom. And if I wanted to know the area that I cleaned, the clean area here, well, all I would have to do is multiply the width times the distance that I pushed it. Whatever this length is and this length is, in this case, these two are the same. Now, what about this over here? In this over here, we've pushed the broom, but the broom curved. Now, we still have our width in the back going around, but now we've got two different distances. We've got a distance from the top and the bottom, which didn't move. We kind of had a curved situation like this, where one place stayed at the same place, the other one moved. Now, in order to find this area, we'd still want to have the width times the distance. But in this case, how far did the broom move? Well, this part of the broom up here moved this whole way over here. This part of the broom didn't move at all. This part of the broom moved less than this. And this one moved more, a little bit less. There's a changing distance that the broom made. Now, the cool thing about this is we can find the distance that the broom moved on average by adding the two extremes and dividing by 2. So we can say that the area equals the width times the top plus the bottom divided by 2. Now in this case, the bottom is 0, so it would just be the top divided by 2. Now, our first example says that as the radius CA turns, it sweeps the area of the circle. So we have a radius over here, CA, going from the center to the outside. We have a distance of 5 centimeters here, and we're told that if this were to go around, it would sweep the entire area of the circle. Now, how wide is that broom? Well, we can see in the picture that it's 5 centimeters. How far does point A move in a full turn? Well, if this went all the way around back to itself, that's a circumference. Circumference is equal to pi times the diameter, or 2 times the radius times pi. Now, the radius we set up here was 5. So we're going to have pi times 2 times 5. 2 times 5 is 10. So we'll have 10 pi. How much does point C move? Well, as we move around point C, C moves 0 centimeters. Which means that when we find the average, if we add 0 plus 10 pi and divide by 2, you're going to get 5 pi, because 0 plus 10 is 10, and 10 divided by 2 is 5. Now, we found the average distance. The average distance was similar to this formula up here, right? Now we can take the width of the radius and multiply it by that average distance, 5 pi centimeters, and we can say that our width of 5 centimeters times the 5 pi centimeters will give us 25 pi centimeters squared. And now you'll notice here that if we had just done the formula for the area of a circle, area equals radius squared times pi, the radius is 5, area should equal 5 squared times pi centimeters squared, and that will give us 25 pi centimeters squared. And it did. Now, the cool thing about this is that this has given us the same area of a circle without using the formula for the area of a circle. We're finding a way to think about areas spatially, as they might have been thought about before we had the formula for the area of a circle. Because somebody, at some point, figured out how to mathematically find the area of a circle, and this is probably a good idea of how they got there. Now, our next example is example 2. Example 2 asks us to calculate the lateral surface area of the cone. The diameter of the base is 2 inches, and the slant height is 4 inches. Now, if we imagine that there was a broom that was as wide as the slant height, going from A to B, going all the way around this cone, then it would stay stuck at point A, and point B would move around the bottom of the circle. Now, point A, the end on point A, wouldn't move at all, and the end on point B would move around exactly the circumference distance. So we've got the A end plus the B end divided by 2, the average distance of the broom, times the width of the broom from A to B. Now, we said that A isn't going to move at all, so it's 0. B is going to move the circumference, which is pi times the diameter, so 2 pi, divided by 2 because we're finding the average, multiplied by 4. So we're going to have 2 divided by 2 is 1 pi times 4 inches, which is 4 pi inches. Now, if we were to describe the variables that we put in here in this equation using the language of math, we could actually use this description, this discussion of the description of how to find the lateral area of a cone to find the formula for the lateral area of a cone. Because it doesn't just work when it's 2 and 4. The point on top, the apex, will never move, and the point that moves along the base will always be the circumference. So we can say that A is always 0, the B end is always the circumference, or 2 times pi times radius. AB is the slant height, or this cursive L. Now, if we plug those in, as we had up here, 0 plus 2 pi r over 2 times the slant height, the 2's here will cancel, giving us pi times radius times the slant height, or radius times the slant height times pi. And that's the formula for the surface area, or the lateral surface area of a cone. So you can see how we can use this idea of area as sweeping to find the area formulas of shapes that we already know. The cool thing about this, and I think it's the coolest thing about this, is that thinking about area as sweeping can help us find the surface area of compound shapes or irregular shapes, things which aren't exactly a cone or a cylinder. If we can break it up into different pieces that are cones or are cylinders, and we can figure out how we would sweep their surfaces, then we can find their areas. Now, this has been lesson 114. I hope you all stay safe, stay inside, and wash your hands.